One of the main concerns of our civilization is air quality. Human activities, as well as natural processes, release in the atmosphere vast amounts of chemicals. Some of these may harm the health of people, other living beings, and affect critical processes occurring in the environment. Hence the great attention placed onto what happens to tracers of any kind, after they have been emitted. The complex phenomena by which things released into the atmosphere spread, and possibly fall to the ground, is named dispersion. To any practical extent, the dispersion occurs within the lowest part of the troposphere. The thickness of this part, named planetary boundary layer, spans the interval from some tens of meters on nighttime, to 1 or 2 kilometers in the bright, good weather daytimes. As tracers tend to remain in the planetary boundary layer, if released there, the smaller its thickness, the larger the concentration. Conversely, if the planetary boundary layer is wider, the concentration gets lower. The phenomenon of dispersion, by and large, may be imagined as composed by various sub-phenomena. Long-range transport, due to the mean wind. Diffusion, due to turbulence. Deposition, also known as fallout, due to settling and precipitation. And chemical reaction of the tracer, with other constituents of the atmosphere. Air is transparent, and most tracers too are, as their concentration decreases or changing thermal conditions make them invisible. So, how to predict ground concentrations? One way is by measuring. But measurements yield useful information only at points where the measurements are taken. Another is by modeling. So you may get spatial distributions, but by simulation, which is not the reality. Whatever the way one decides to use, the problem remains. The reality of dispersion is intricate and difficult to figure out. This is especially true in urban settlements, where buildings and other features make up a complex shape for wind to pass through. And in this part of the movie we can see why. There are sudden changes in time. Non-uniformities in space. Plumes change shape, as they open up due to diffusion, and drift due to transport. Here you also can easily see how the plumes, white, that is, mostly composed of water, become quickly invisible with increasing dilution. And buoyancy? In this image its effect appears minimal, and overlap with downwash, caused by wing profile effects due to roofs. In conclusion, we are facing a fascinating, intricate world which, to date, is still being investigated by modelers. To us, as final users and citizens, the important task to make ourselves aware and informed of all this. This can be accomplished by studying the minimal grounds of the physics of the lower atmosphere. But now it's time to close. Thank for attention, and see you next.